Hello everyone, welcome to VLSI Toolbox. Today I will be discussing about how to design a differential amplifier using GPDK90nm technology. So without wasting time, let's go to the design process. So this is the basic differential amplifier. This is the basic differential amplifier where I have marked these pairs with separate color because M1 M2 are equal in size, M6 and M5 are equal in size, M3 and M4 are equal in size. Again, I like to mark another thing using ICMR plus specification. We can find the aspect ratio of these two MOSFETs. Using GPW specification, that is this one, we can find M1 M2 aspect ratio. Again, using ICMR minus, we can find the aspect ratio of this M6 M5, and using slew rate specification or power specification, we can find the reference current value. So these are the design specification. DC gain is 40 dB, GPW is less than 30 megahertz, phase margin is 60 degree, slew rate is 20 volt per microsecond, that is rate of change of output voltage, and these are the range of input DC bias voltage with which we can keep the M1 M2 in saturation. That is ICMR plus maximum voltage, common mode voltage we have selected 0.8 volt, ICMR minus minimum 0.4 volt, the load capacitance is 2 picofarad and 1 volt is the supply voltage, and these are the process parameters. I have made separate videos for this, how to calculate this, without which you cannot design the amplifier. So before going to design the amplifier, we should know the values of BP Cox and mu1 Cox. These are process parameter. BTH of NMOS, BTH of PMOS we have to find. So I have given the link in the description. You can go through this video first and then proceed for designing the differential amplifier using this video. So let's design the M1 M2 and reference current first. So using GPW specification, as I have already told, we can find the GM of input required GM of input pair, and using this GM, by using this formula, we have found the aspect ratio of M1 M2 to be 12. This needs to be tuned further depending upon the specification of GPW. If GPW is not met, then you have to tune the aspect ratio. We have to increase the W input pair W. We have to increase the input pair W to meet the GPW specification. This is the relationship of slew rate with current and load capacitance. Using this, we have found the required current to be 40 microampere. Again, I like to highlight the load capacitance 2 picofarad is the overall capacitance at the node V out. That is also intrinsic capacitance is also there. So we have to adjust the load capacitance to compensate the intrinsic capacitance to get exact slew rate in the simulation. Next is the design of M3 M4, that is load transistor. Using this diagram, you can also visualize, that is, if BD1 is greater than equal to BGS1 minus BTH of 1, then M1 will be in saturation. Again, BGS is the B in max, that is, using ICMR max we can find the aspect ratio of M3 M4. So B in max minus BTH 1. So in this way I have found the required BD1 voltage to be 0.616 volt. So using this I have found the values of BSG3 or VSG3 because it is a diode connected. So BSG3 is equal to BSD of 3. So in this way we have found the values of VSG3 to be 0.384, and using this formula we have found the aspect ratio to be 5.1. Next is the design of M5 and M6. Using this relationship, we have to find a BD set of 5 for finding the aspect ratio of M5 and M6. As you know, we have to keep the B in, that is common mode bias voltage, minimum voltage, greater than or equal to the summation of BGS1 and BD set of 5. So using this we have found the values of BD set of 5. For that, first we have to calculate the BGS of 1 from previous calculated values, and B in minimum is the aspect specification, that is 0.4 ICMR minimum, and using this we have found the values of BD set of 5. Our BD set of 5 is further put in this equation to find the aspect ratio of M5 and M6 to be 23.41. And this is the summary of all the designs. I have calculated the aspect ratio of M1 M2 to be 12 macro by 1 macro, and aspect ratio of M3 M4 to be 5.1 macro by 1 macro, and aspect ratio of M6 and M5 to be 23.41 macro by 1 macro. I have kept the length 1 macro constant, CL load convergence 2 picofarad, I5 40 macro, and common mode voltage is slightly kept higher than the minimum ICMR 0.415 volt. This can be further tuned to meet the slew rate. Actually, for getting the exact tail current, you can tune the common mode voltage, so to get the exact tail current if there is a mismatch in the tail current. And I have used all the equations from this book, so please refer it for further clarification. Now let's move to the demo and see how the calculated value can give the expected specification, that is design specification. So let's move to the demo. And one more thing I like to say, please visit the video link provided in the description, which will be required for you, that is how to calculate mu and Cx, mu p Cx. All video links I have put it in the description. Please visit first before going to design the amplifier, differential amplifier, or before going to follow this video. So let's move to the demo and see how does it works. So open your working folder, right click, open in terminal, CSH, source the script file. In my case, this is the path. Type virtuoso. So cadence is open. This is the CIW window, cadence console window, you can say. There is a file manager. Now go to file, new, library, differential amplifier, you give any name. So I am giving the file library name like that, attached to an existing technology library. Use the GPDK90. So this is the blank library created, and selecting this, go to file, new cell view. So new file, give a name, diffamp. So this is the schematic creator. Now you draw the circuit. Press I, go to GPDK90, NMOS 1 volt VDD. So hide, place it here for input pair. Then again I sideways to flip the MOSFET. Next, another NMOS is required for current mirroring, sideways. This is a tail MOSFET. Now press escape, again press I. PMOS load, for load, M3 M4, sideways. Now press W to wiring, complete the routing or wiring. This is the input, which is for BDD. This is for ground. This is for IBIS, bias current. From this branch, we will take output. So as of now, drawing is complete. Now let's connect the pins. Click on this symbol, create pin. So for input, B in plus, B in minus, this will be plus, this will be minus. B out will be our output pin, and BDD and ground. These are power pins, BDD, ground. So this is the complete circuit. Check and save. Now according to our calculation, let us put the values. ISS is remaining, so keep input pin ISS as IBIS. Now check and save. So let us put the values according to our calculation. So select both these input pair, press Q, apply to all selected, keep the width. I am keeping length to 1 micro constant, width to be 12 micro. Similarly, selecting this two pair, PMOS load, again length is 1 micro, width is 5.1 micro. Next again select these two, press Q, length is 1 micro and width is 23.41 micro. Check and save. Parameter is given. Now let us create the symbol of this. Go to create cell view. From cell view, now ISS you can put along BDD and ground you can put in the bottom. Press OK. So this is the symbol. So you can delete this and draw the symbol of amplifier by selecting the wire. Select this, drag, you can arrange according to your convenient. Close it, close it. Now for simulation let us make one test bench. Press I, go to your folder library, use your symbol, press I, go to analog library, press PDC for voltage source, 1 volt power supply, BDD, ground, and for 2 inputs these are for load capacitance. Press IDC. So according to our calculation current will be 40 micro. So these are the inputs. Now let's connect the load capacitance cap. As per our calculation, this is 2. Pin, output pin, B out. Check and save. Now let's configure the input. Give the common mode voltage as per our calculation. According to our calculation, a minimum ICMR is 400 milli. So let us keep slightly higher than 400 milli. Later on I will show you if I keep 400 milli, then what does it happen. Apply and give one AC magnitude for AC analysis. Negative terminal AC magnitude is not required, only bias voltage. Check and save. Now let's do the simulation. Go to launch, ADL, setup, check the model libraries, uncheck all other model libraries, only keep GPDK90. Analysis, choose DC analysis first to check the operating points. Next is our AC, 1 Hz, 200, 1 gigahertz, let's say. Logarithmic plot, 100 points per decade. Then run it. So this if this either come effective length is less than equal to 0, this is due to the scaling problem. So let's fix it out. Go to output, go to simulation, option, analog, component, scale, you just change it to 1. Now run it. It's okay now. Now let us first check the regions of operation of all the MOSFET, whether it is in the region 2 or not. Our main objective is to keep all the MOSFET in saturation. Click on this, open a new tab. So now let us annotation, go to annotation, right click on it, annotation, DC operating point. It will show all the currents distribution along with BTS, BGS, GM, everything will be shown here. Now we want to show some extra parameter, that is region. So let's annotate, click annotation, setup, GPDK, say NMOS, click in the blank, give region, apply to all. Next for PMOS, similarly. So you can see here these two PMOS are in region 2, along with inputs are also in region 2, and also the lower tail MOSFETs are also in region 2. So our main objective is fulfilled. Now if you want to check that if we decrease the input common mode range, that is if you give 400 milli, the minimum that we have selected for our calculation, you can check it, run it and check the region. See, this MOSFET is now in the region 1, which is not desirable. For that we have just given minimum amount of voltage, for that our all MOSFET are in saturation. Check and save, run again. See, you can see here this is in region 2. So first objective is cleared. Now let us check the gain. So again run it, go to result, direct plot, AC gain and phase. So B out by B in. See, This is the gain. As per our calculation, 40 dB is expected, so it's coming like 40.84 dB. And check the GBW, 23.77, less than 30 megahertz, less than equal to 30 megahertz, so it's maintaining. If you want to increase the GBW, then you have to tune the input pair W to increase the width of the input pair. Then GM will be increased, accordingly GBW will be increased up to 30 megahertz. So it is a matter of tuning. So now our another crucial parameter is the slew rate. So let's check the slew rate, how much it's coming. So for slew rate, we have to change the setup. Make it as unity gain buffer. Change the input to pulse, B pulse. Suppose 900 milli maximum voltage, period say 5 micro, pulse with 2.5 micro. Press OK. Now we have to add another analysis. Go to analysis, choose transient 20 micro, more than the period. Click on conservative, then done. Okay, then go to result, direct plot, transient signal. Click on the B out, press escape. So it will come like that. Note the maximum voltage 855.56 milli. Minimum is 36.79 milli. So let us calculate the slew rate based on this maximum and minimum. Click on the waveform, send to calculator, function, go to slew rate. So initial value is how much? Minimum value is 36.79 milli, and maximum final value is 855.56 milli. Press OK. Now calculate 17.76 volt per microsecond. So we have designed the amplifier for 20 volt per microsecond. It's coming 17.76. This mismatch is due to the intrinsic capacitance of these two MOSFETs. So that is intrinsic capacitance is also coming with 2 picofarad. Means there is actually the actual capacitance is more than 2 picofarad now, as of now. So to compensate it, let us change the capacitance little bit lower, 1.8, so that in total 2 picofarad can be realized. So I am just arbitrarily reducing the capacitance to see the effect in slew rate. So run again. It is taking time. Okay, now go to result, head plot, transient signal, click on Vout, just escape. Voltage, maximum voltage is same as previous, 34.82, minimum is changed. So go to calculator, function, previous function you can also click from here and just check the verify the minimum, 34.82, 34.82, just give 34.82, 82, calculate. Now you can see it's increasing, 19.64. So in this way you can also include the intrinsic capacitance along with the load capacitance to make the output total load capacitance as 2 picofarad according to your specification. So we have to also include the intrinsic capacitance of the two output MOSFET. So this is it from the demo point of view. All other analysis are there in my channel. Please visit my channel and watch the related videos in my playlist. So hope you have found some valuable information from this demonstration. Please keep liking my videos and sharing, and please subscribe my channel so that you can get more such videos. Thank you.